Thanks, everybody. Thank you, sir. All right. Thank you, thank you. All right. Well, let me begin with a word of prayer. And we'll get into it. Heavenly Father, we thank you for this day. Again, I thank you for this class and these students. Just ask you to bless our work today. Help us to glorify you do what we do, and just understand a little bit more about set theory, Lord. In your name I pray, Lord Jesus. Amen. All right, so I decided to try to do some examples today which aren't in the notes, so then you can read the notes and understand them. I will say that as a point of like logical clarity, there's something a little bit askew with example 3.34. So before I forget, let me just make a comment, which is in example 3.34, logically speaking, I need to say also define a sub 1 over n equals to 0, comma 1 over n. Otherwise, technically, I haven't defined this symbol, yet my proof involves it. So a simple fix to that example is just to put that in the initial sentence. Then I think the rest of it actually is logical. All right. That notation is not at odds with the rest of the example, because in the example, for example, we have like n equals to, this is for n greater than or equal to 2 in the natural numbers. Notice that like if we put n equals to 1, then you might say, well, 1 over 1 is 1. Does this comport with that notation? Well, that example I have like a sub 1 is 0 to 1. So this notation and the notation that's already in that example, they work together. And you should be able to read that example with understanding with that modification. All right, so anyway, that said, I thought it'd probably be helpful for you to see me work a less trivial example, because that example is pretty trivial. This one is slightly less trivial and more like your homework. So let's work this one. So how do I prove that the intersection n equals 1 to infinity of a sub n is equal to 3, given that my a sub n is the open interval that goes 3 minus 1 over n to 3 plus 1 over n. How do we prove something like this? Well, the proof goes in 2 steps, right? So first, I'll say, notice that 3 minus 1 over, oh my bad. Notice that, let's just say it this way. 3 is an element of 3 minus 1 over n to 3 plus 1 over n for any n in the natural numbers, since what? 3 minus 1 over n is less than 3 is less than 3 plus 1 over n for any n, right? I think we can all agree on that inequality. Like, I don't need to try to prove it from something more basic. Are we in agreement? Is this clear? I hope. 3 is there. All right. So what does this mean? Thus, x, an element of the set containing 3, implies what? X is equal to 3, right? This is kind of silly, but there's only one element in there, which implies that 3 is an element of the set 3 minus 1 over n to 3 plus 1 over n, which, by the way, we defined to be a sub n for what? All, I kind of like each better, this word here, for each n in the natural numbers. But what does this prove? If 3 is an element of a sub n for each n in the natural numbers, well, 3 is a natural number, that's true, but not the point. What does that say about this here? We just proved that 3 is an element of a sub n for every possible n. So by definition of the infinite intersection, what do we have? 3 is an element of the intersection n equals 1 to infinity of a sub n, right? That's what it takes to prove something's in the infinite intersection. You have to establish that that element is in every subset that's intersected, right? Every set that's forming the intersection. So what does all this show? What do we got then? So I guess I'll write over here. Therefore, the set just containing 3 is a subset of what? Of the infinite intersection, right? I'm trying to prove that these two sets are equal. Now I've got half of it, right? I need to get the other side of the containment, right? So what's next here? Next, suppose x is an element of the intersection n equals 1 to infinity of a sub n. Right? Then what does that mean? X is an element of a sub n, which I'll write out what that is. A sub n is equal to 3 minus 1 over n to 3 plus 1 over n, right? For every n in the natural numbers. So what does this tell us? What does this mean? Consequently, what? We have, what inequalities do we have? We have 3 minus 1 over n is less than x, which is less than what?
3 plus 1 over n.
3 plus 1 over n for each n in the natural numbers. So we'd like to show that that implies that x has to be 3. Right? How can we prove such a thing? I mean, first of all, I would grant that it's intuitively obvious that that's true. Right? How could we give a more convincing logical argument? You have an idea, Christian?
Is it reasonable to just set up a limit that approaches infinity and show that it like that?
Oh, that's actually very helpful. I wasn't thinking about that, but I like that a lot. We've all had calculus 2. Calculus 2 is a prerequisite. It is reasonable at this juncture to use theorems about sequences that we learned in calculus 2. One of those theorems we learned was we have a comparison test for limits of sequences, right? So we're looking at 3 sequences here, right? One of them's kind of boring. We have, let me call this sequence a sub n. We've got this sequence we could call perhaps little b sub n. The third sequence c sub n, right? And let me point out the structure here. We have a sub n is less than or equal to, well, not even less than or equal to, less than. B sub n is less than c sub n, right? For all n in the natural numbers. And where I'm saying b sub n is the constant sequence x, right? Note the limit as n goes to infinity of 3 minus 1 over n is equal to what? 3, right? And the limit as n goes to infinity of 3 plus 1 over n is equal to 3. Hence, by squeeze theorem, the limit as n goes to infinity of b sub n is equal to 3, right? But the limit as n goes to infinity of b sub n is just equal to what also? It's just x, right? And that, of course, the limit of a constant sequence is just the constant x. So, hence, x is equal to 3. I like that. That's a decent argument. I kind of like that, actually. And okay, so if you'll let me continue in a different font over here to finish the argument. I mean, different color font. Probably the same font. I am who I am. But let's see, finishing then. Thus, x equals to 3 is an element, of course, of the set containing 3. And so we have that the intersection n equals 1 to infinity of a sub n is a subset of the set just containing 3. Consequently, by double containment, we find that the intersection n equals 1 to infinity of a sub n is just equal to the set containing 3. And there you go. So there was a connector here. All right. Yeah. Would you like to see the stupid argument I was thinking about if we didn't use limits? Here, I'll show you. Here's a way to do it without limits. So without limits, and I'm not sure this is even better. It's just a way. Without limits, if there exists, suppose there exists a delta greater than 0 for which x is equal to 3 plus or minus delta, and 3 minus 1 over n is less than, x is less than 3 plus 1 over n for all n in the natural numbers. Then this would say what? What's the thought process behind what I just wrote in brown? What am I after here? My goal is to show that there does not exist such a delta. Because to show that there does not exist such a delta is tantamount to showing that x has to be equal to 3. Right? If I can show that there's no way to write x as 3 plus or minus a delta for some positive delta, it must be that x is 3 by process of elimination. Every real number is either 3 or it's plus or minus something from 3. Plus or minus some positive thing from 3. So what do you do with the blue inequality? What do you do? Just subtract 3 across the board, right? This implies that minus 1 over n is less than plus or minus delta is less than 1 over n, right? Which then implies that minus 1 is less than plus or minus delta times n is less than n if I multiply that by n. Yeah.
Less than 1.
Oh, yeah, thank you. Very good. Yeah, if I could just do what I think if I could write what I think rather than what I write. Anyway, so this is impossible, right? We can't have a number that is between, let's see here, how can I say this? So this, maybe we have to break up into the plus case. So like the plus case, right? We have minus 1 is less than delta n. I guess that's not a problem, right? But how about the minus? We'd have what? We'd have minus 1 is less than minus delta n. Which would then tell me, I don't know, maybe this isn't a problem. Oh, man. I'm sorry, I'm not as confused as I was hoping I was. Do you guys see it's a contradiction? I was hoping I'd find an obvious contradiction here. Maybe I didn't. I'm talking myself out of it now. Let me go back to this, actually. Let's go back to this here. Anyway, I don't see it now. I don't see it. I guess we have to go to your limit argument. Maybe you guys can give me a convincing end story to this, right? So let me just leave it. Here's a bonus point opportunity. Bonus point. If you can email me a convincing contradiction from, to complete this argument. And show there does not exist a delta greater than 0 such that x is equal to 3 plus or minus delta. All right? I'll leave that as an open project for you guys rather than squandering more class time on it, since we already have a good argument over here. So this, of course, is part of... don't you try to restart my computer right now. I'm not going to pick a time. I'm going to close your restart, pick time. Haha. Take that, Windows. Anyway, sorry. So, this is part of mathematics. You try something. It works. Sometimes it works. Sometimes it doesn't. Maybe it still works, and, you need to talk to a friend who's like, it works. So, I'm trying to count you guys as my friends. So help me out by email. So my next thing for class here is this theorem. Can you guys tell me what I'm writing here? What's this over here? We have U is the universal set. A is a subset of the universal set for each alpha in the index set lambda. Then the complement of the union over alpha, right, is the intersection of the complements. And how about this? Number 2. The complement of the intersection is the union of the complements. But you notice here that these are over arbitrary unions and arbitrary intersections, right? I stated this for 2 sets before. That was what? That was De Morgan's laws, right? Remember this? So this is what I'm telling you is, in fact, De Morgan's laws extend over arbitrary unions, all right? And I'm going to give you a proof of this, actually, that is, so we've looked at a lot of double containment proofs so far in here, but here I think I can manage a, what you might call a biconditional proof. So I'm going to give a proof which shows you that these 2 sets have the same elements, and we're going to do this with a string of biconditionals, all right? So if you can manage a proof like this for a given problem, it's super nice because it's easier, all right? So here's the proof. And so what we're going to look at is like this string of equivalent statements. To start with, x is an element of the union over alpha and lambda of a sub alpha, complement. All right. So by the way, to be clear, I'm assuming the conditions of the theorem, all right? So you'll forgive me for not writing that in my proof this time. This is true if and only if what? X is not an element of what? The union, right? What does it mean to be in the complement? It means that you're not an element of the set, right? This is one way we can state the definition of complement. But what does that mean? And do you agree that this is, this is a reversible arrow because this is essentially the definition of the complement of that set, all right? So I have both directions here. But this is true if and only if there does not exist alpha in the index set lambda such that what? X is an element of a sub alpha. Does that make sense to you guys? if there was an alpha, right, for which x was an element of A sub alpha, then it would be in the union, by definition of union. So to say that it's not in the union is to say that there does not exist even one index for which x is contained within the set indexed by that index, which is what I've wrote. So then what? Well, we can make a little bit more. What does this mean? Well, this means, another way to look at this is that x is an element of the complement of A sub alpha, right? For each alpha in the index set, right? Here I'm using the tautology that allows us to swap the existential quantifying for the for all quantifying, right? If there does not exist one such that, let me just put it in words here. So what I'm saying is that x, what does this mean? X is an element of the complement of A alpha. That means that x is not where? No, x is not where. X is not in A sub alpha, right? Is that true for every alpha? It's true because right up here we have there does not exist an alpha for which x is in there, right? So there's not even one which contains x, which is to say that every alpha has x in its A sub alpha. Every A sub alpha has x in its complement. So then what? What does that mean? We have x as an element of A sub alpha complement for every alpha. That means that x is where? The intersection, right? Of the complements. So, just to be clear, going from here to here, back and forth from here to here is definition of the intersection over alpha, right? Well, let me write it like that. It's the definition of the intersection over alpha and lambda, right? That's the logical connection between those last two steps, right? So what does this show? Every point which is in the complement of the union, right, is also a point which is where? In the intersection of the complements, which shows you that these two sets, which I'll underline in red here shortly, have the same elements, right? But if two sets have the same elements, then what?
Same set?
They're the same set. So this proves what? This proves 1, right? Claim 1 follows. Since we've shown that was supposed to be shown, it became shown or something. Shown these sets have same elements. All right, help me out. How can we prove 2? Oh, fair enough. We could go through a very similar, point-by-point argument, just like we did. I wanted to be lazier. Is there a way we can prove 2 using that, let's say any set, right? Subset of U that has what? S complement is what? S, right? So what if I look at, I usually do some kind of boneheaded thing here, but let me try. So union over alpha and lambda of A sub alpha is equal to the union over alpha and lambda of lambda a sub alpha complement, right? Because if we take the complement of the complement with the other set again, but what can I do with the first complement? I can use, can I use 1? Aw, man, maybe that doesn't help. I'd hoped I could use the this to get the other one. Maybe I can't. Maybe that's just wishful thinking. I have some vague memory of when I tried to do these are homework problems in another book, and I worked it like 10 years ago, you know? So I have some fuzzy memory of like getting the other one from the other one, but maybe my memory's wrong. Because I don't know how to do anything yet with that.
You start out with the union instead of the intersection.
Start out with the union instead. Okay. If I start out with the union, I like that. All right. Then what? Then I can use 1, right? So I think I need to start out with the union, but I need to be sneakier than that, right? Because what I'm after for the proof of 2 is what? The union of the union of the complements, right? So I need to be slightly more sneaky. Right idea. Let me be slightly more sneaky, which is start out with what we're trying to prove, which is this, right? So let's put some complement. Let's complement this thing, right? So, yeah? Yeah? All right. Now, great idea. So that means just focusing on the first complement, we have the complement of the intersection over alpha and lambda of a complement alpha using 1. But understand that I'm using 1 with a substitution, right? Like the complement of A alpha is still a subset of the universal set for every choice of alpha, which means that the argument for 1 still equally well applies, all right? Then we'll use the complement. So this, of course, is A alpha, which gives us, and we're done. Because that is what we're trying to prove, that the complement of the intersection is the union of the complements. Thank you, guys. I was stuck. I was about to waste a colossal amount of class time on that. So. Very good. All right. So I hope these help you. One other thing I should mention for the sake of like something that might be helpful for the homework is something called the floor function and the ceiling function. So I want you guys to read the notes, all right? So I don't do all the examples in my notes in class all the time. I usually do a lot of them in here because I don't have that many notes for this class. But for that reason, sometimes it's probably better for us if I invent some new examples for class, right? To expand the universe of our discourse. But I should give you this definition because you might not have thought about this. And so here it is. The floor, so let y be a real number, then floor, oops, there's putting 2 L's in floor, that's not a good sign. Floor, the floor function of y is, so we do this like sub-bracket y, see this? It's like vertical lines with like little legs down here. This is the floor of y. And we're going to define that to be, it's defined to be the element of y minus 1, comma y. Y is included, but y minus 1 is not included. Intersect with z. All right? And also we can talk about the ceiling function. This is not in the notes, but I probably should put it in the notes. My bad. Ceiling function of y is, so like instead of the upper feet, like the ceiling, like that. That would be an element of, I think we want to include y and exclude y minus 1 I feel like these might be backwards, guys. We need to. They sound like they. I'm very. Well, let's see if these definitions are right. Yeah. that usually doesn't make sense, right? Is the definition right? Is a question which doesn't really make sense in mathematics unless the instructor makes a typo on the board. You know. Because the definition is what it is. It doesn't have to explain itself further. Unless it begs logical questions like, you know, it sets up an absurdity or something. But okay, so let's see here. I'd like to say that the floor of like, you know, 3.7, I would like for that to be an integer which is smaller than 3. Does this do it? Is this the intersection of? So this is supposed to be the intersection of 2.7 with 3.7 intersected with z. I think if you look at that, that's the set containing just 3, right? Okay, so it's right. My intuition that it's wrong is just wrong. Yay. Notes are okay. Yep.
I think for the ceiling function, it needs to be bracket y comma y plus 1.
So you're going to argue in a +1 here?
I think.
Okay, let's try your definition out. I like it. So let's say the ceiling function of, let's say, 4.8, right? I want that to be an element of, according to your definition, which I'm hopeful, I want you to win. I want to be wrong. I like for me to be wrong and the students to be right. That is, because I don't need points. You guys need points. Let's see here. You know? So if we do 4.8 to 5.8, intersect with the integers, there's only one whole number in here, namely 5. This is equal to the set just containing 5. Yeah. Thank you. Very good, Nolan. Excellent. So this is the ceiling function and the floor function. This is very helpful if you're doing an argument and you need to pick the next natural number past where you are, right? So these kind of functions could be super useful if you're trying to do something silly like, here, let me just give you a simple application. What example am I on? One, I guess this was a theorem, it's not an example. This is example 2. Like, for example, the union n equals 1 to infinity of, you know, 0 to n is equal to 0 to infinity, right? So if x is an element of the union n equals 1 to infinity of 0 to n, then there exists n in the natural numbers such that what? X is an element of 0 to n, right? Which implies that x is greater than or equal to 0, which implies that x is an element of 0 to infinity, right? Thus, union n equals 1 to infinity of like 0 to n is a subset of 0 to infinity. Now this string of thoughts did not require anything terribly nuanced, right? That was just, we're just sorting through the definitions. Obviously, the union is a subset of the set of non-negative real numbers, right? The other direction might require a little bit more sneakiness. So let x be an element of 0 to infinity, right? Then what does that mean? X is greater than or equal to 0. If x is equal to 0, then 0 is an element of 0 to 1. Therefore, 0 is an element of the union n equals 1 to infinity of 0 to n. It's not 0 I'm so much interested in, it's x. All right, the x which is equal to 0 is an element of the union. If x is greater than 0, then what does that mean? You guys still don't need the floor function. I'm not sure I really needed to separate out the x equals to 0 case, you know. My intuition was I should separate out x equal to 0 case, but my intuition sometimes serves me wrong in here, guys. How about x greater than 0? Can you give me... all right. I just, let me put some big red parentheses and go dumb. I'm gonna call an audible. That was just dumb. I didn't need to do that. Because, check this out. I should have asked you guys, you'd have told me what to do. If x is an element, 0 to infinity, then blank is an element of the natural numbers. And blank is greater than x. What should I put there? How can I get a natural number larger than x? X what?
Ceiling of x.
Oh, the ceiling of x, okay. Yeah, ceiling of x, right. I thought you said x0. I was like, wait, what? But it's just me. So ceiling of x. And the ceiling of x is greater than, is greater than x. Thus, x is an element of 0 to the ceiling in x, right? Therefore, x is an element of the union n equals 1 to infinity of 0 to n. In other words, let n equal to the ceiling of x, okay? That's a specific natural number which x is in, and if it's in any one of them, it's in the union by definition of union, right? So, thus, 0 to infinity is a subset of the union, n equals 1 to infinity, 0 to n. Hence, by double containment, we're done. All right? Yeah.
Could x be equal to the ceiling of x also, or no? Like if it's already a natural number?
Let's see here. If could x be equal to the ceiling of x? Yes, that is true. As we've set up the ceiling function, yeah. So I don't have a strict inequality, I have a what? Thank you. Good. I should say this is what? Greater than or equal to. Right. But the argument still works, right? Yeah.
That was more for my
No, that matters. And if you didn't put that, I should take off a half a point or something on the test, you know, if I'm being a good instructor. Because we want to be precise in here. All right, so. Thank you. Let's see where I am. All right. So we need to move on here. I will do that. So the next topic that we should, there's two topics that are kind of big. One is more important than the other, and so I'm going to do the more important one first, all right? So the more important topic is the Cartesian product. What is the Cartesian product of sets? Do you guys know? No? So, technically speaking, I'm skipping over my section 3.31 here, but I'll probably circle back to it at the very end of class and do it in justice. But anyway, here we go. So this is section 3.4, which is on Cartesian products. And I start with a definition. So And this definition is a little bit technical, and we're not really ever going to use it much, but here it is. An ordered pair is a set of two elements with an ordering. We denote this by A comma B, and technically speaking, that is, which is, equal to the set containing A and then A comma B. There's a fairly decent chance that if you asked like 5 out of 10 math professors to define an ordered pair using set theory, they probably couldn't. Because as a matter of practice, we almost never use this. But if you ask the question, what is an ordered pair? Like, how would you construct an ordered pair? This is a way you could do it. So this is what you might call a model of the ordered pair. The critical thing for an ordered pair is simply this. If we have A1, B1 equal to, well, let's say A1, A2 equal to B1, B2. All right? That's true if and only if A1 equals to B1 and A2 is equal to B2. So an ordered pair has an ordering, and if you have two ordered pairs are equal, the only way they can be equal is if they match up in each of the slots that are in the ordered pair, right? This blue sentence I just wrote is true if we technically define the ordered pair by this set of sets, right? But this is obnoxious. Nobody wants to work with this. I'm just pointing out that you can do it as a matter of what do you mean by ordered pair? Well, you could mean that, yeah.
Why is A in the set? And, well, A and A comma B, but not B?
Because there's a distinction between this versus this. Now this would be equal to, for what it's worth, but anyway, the role of A and B are distinct. That allows you to order the set. Yeah. So if you were to, that would be the mechanics of how to prove this assertion given this definition for ordered pair. Given this definition for ordered pair, you could prove that these are equal if and only if you have this and that because of the structure that A and B appear asymmetrically. That said, we do not want to work with this for the most part. We would like to operate at this level, right? And so, in fact, A cross B, this is the Cartesian product of A and B, is equal to the pairs A comma B such that A is in A and B is in B. So this is the set of ordered pairs, the so-called Cartesian product of A and B. All right? I'm assuming, of course, A and B are sets. What if you had n things, What if you have n sets? A1, Cartesian product, A2, Cartesian product, AN. Could you do that? Well, yes, you can. The Cartesian product of n sets is like this. We have A1, A2, dot, 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 AN, such that, let's say, A sub I is an element of big A sub I, for I equals to 1, 2, dot, 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 n. So we can form not just ordered pairs, we can form ordered, well, these are usually called n-tuples. All right? Notice I'm not even assuming that these sets are the same set or anything. This is an n-tuple, or n-tuple. All right? Two n-tuples are equal if and only if they have matching components. right? Everywhere. So like, if we have A and B are both elements of A1, Cartesian product A2, Cartesian product AN, then A equals to B if and only if, A sub I is equal to B sub I for I equals to 1, 2, for every component. I just used a word, didn't I? A sub I is the ith component of A. You write that down. So this is Cartesian product. Now, you guys have been using Cartesian product in like calculus, right? You talk about R2, yeah? Talk about R3 perhaps if you've been in Calc 3. Even talk about Rn, right? Rn is the Cartesian product of R with itself n times. So definition, if A is a set, then A to the power n is A cross A cross A. This is n-fold times, right? Which is specifically equal to, something like, let's say x1, x2, xn, such that x sub I is an element of A for all I. In the context that we're just taking the Cartesian product of a set with itself n-fold times, we use the exponent notation to indicate what we mean by that. All right? Now there's danger for confusion in this notation for sure. And there's some common abuses, right? So like, technically speaking, the Cartesian product of sets is not associative. Like, let me show you what I mean by that. Actually, before I even get to that, though, I should first warn that there is danger of confusion with interval notation, right? Check this out. You probably already noticed this at some point. But if I say 1, 2, what does it mean? There are two very different uses of this notation, right? The one is that 1, 2 is equal to x in the reals, right? Such that 1 is less than x is less than 2, right? This is the interval 1, 2, which is a subset of R. Right? It's a set containing infinitely many points that range on the number line, if you like, between 1 and 2 non-inclusive. But on the other hand, what else is this? It's an element of what? R2, right? It's a point in 2 dimensions. We use this notation for both things. So you have to know by context which is which. This bothers the French so much that they refuse to use this notation. In some French mathematics, so I guess a lot of it, you'll find this. If you use this notation in my courses, I'll take points off. We're not French. I'm just kidding. I probably wouldn't take off points off, but I'd be like, did you grow up in a French-speaking place or something? Like, I don't know. It's just, to me, it's a very awkward notation, but I see the reason. Yeah. So that's one thing. The other thing, and this won't bother any of you for the most part, but check this out. If I had A cross B cross C, or if I had A cross B cross C, or if I had A cross B cross C, we could see these as being rather different things. So like a typical element in here might look like A, comma, B, comma, C. So it's a pair of a point with another pair in that order. Whereas a typical element in this guy would be something like a pair paired with a point in that way. Right? So as a point of order, we don't really distinguish between these things in usual mathematics. Like we identify these all the time. And so if we don't really care, we could just write A, B, C. And that could be, this would be, so what I'm trying to say is we identify these as a point of common custom. Technically speaking, they are distinct objects, right? They are. So you've been warned. But also you've been freed not to fuss over the distinction between those objects, unless I ask a question which is specifically about fussing about those objects. But anyway. Okay, so, great. What are the properties of Cartesian products? And can I give you an example of something that's like a little bit more interesting? I think I can. Example 3. So let's use interval notation. What would 0, 1 squared mean geometrically as a subset of R2? Can you picture this? What is that? I'll draw a picture for you. What that is the unit square. See, because if x comma y is an element of 0, 1 squared, right? That means that x is an element of 0, 1. Well, excuse me, one more step here. That means that x comma y is an element of 0, 1 Cartesian product with 0, 1, which is to say that x and y are elements of 0, 1, right? Which means that the value for x and the value for y are ranging between 0 and 1. Well, what is that? Well, that's a square, right? So the unit square in Cartesian product notation is just 0, 1 squared. Example 4, let's make something a little bit more interesting. What if I had, like, I don't know, minus 2, 2 Cartesian product with, say, 3, 4. What would that look like? Let's graph it. So that means that that set, right, x is ranging, so like if x, y is in this set, implies what? That implies minus 2, well, it implies x is an element, minus 2, 2, and y is an element of 3, 4. Tell you what, let me make this slightly more interesting. Let's fuzzify the 4. We'll make this 4 not included. There we go. So what do we got? Minus 2 less than or equal to x less than or equal to 2, and 3 less than or equal to y strictly less than 4. So the way I graph something like that, right, is I draw a solid line. First of all, I identify the corner points. So like minus 2, 3, something like here, and then, my bad, something like here. I'm trying. So that point is minus 2, 3. And then over here, there's another point, right, like 2, 3. And then we got like up at 4, we've got like minus 2, 4, and then over here, 2, 4, right? Those are the corners. This is a rectangle, right? And it's got solid edges on the top and on the bottom. And also over here, where y is equal to, oh, wait a minute. I can't do, my bad. What is the top edge? What's the top edge? It's where y equals to 4, right? That's not included. So to denote that, we do this kind of deal, right? And then, but x equals to minus 2 and x equal to 2 are included, so I do solid edges over here, right? And then everything else in the middle. So that's a picture of that set. This lecture, this thing is trying to get me every day. It's trying to get me. Anyway, are we good? Now, Cartesian products have many interesting properties. And I should tell you about those, I suppose. I probably should use the projector, though. I think we're running short on time here. I will probably prove a lot of these things next week, but I need to tell you about them. Some of these things are in the homework, so you don't want to work on them. I think you can work. I think we have done enough in here that it should make sense to you, even if I don't lecture on it in its entirety, because these things are. Well, for one thing, you've seen them, a lot of them, in previous classes. We're just being more careful about that. That's one aspect of it. One significant caveat to that comment is the topology. That is genuinely new. But really, the homework problem you have on topology is not that deep. But you do have to work with the definition. Now, if you get stuck on that, you come and ask me about it. I'll help you. If I can find my notes, that'd be lovely. So just to let you know where we're going. So like next time I will, finish proving things about Cartesian products, and hopefully we'll look at some more examples. This time I'm just going to put those up here for a second. We'll look at them together. So like there's some very so my apologies, guys. Today I squandered too much of my time talking about these silly infinite unions, these arbitrary union problems, So I help you out too much with that, and then I don't give you enough help on the other things. So my bad. But anyway, here's some things you can prove, like the Cartesian. If you have the Cartesian product of two sets as the empty set, it means either one or the other of them have to be the empty set. Either A is empty or B is empty. Of course, they could both be empty also. If you have A, B, C non-empty sets, if you have A cross C is a subset of B cross C, then that is true if and only if A is a subset of B. So Cartesian product plays well together with subset. Here's some other properties of Cartesian product, like the Cartesian product of a union is a Cartesian product with a union of two sets is the Cartesian product of the union of A with each set separately. And so here Cartesian product also plays well with intersection. The Cartesian product of the empty set, and we also have these kind of, I guess you could call these sort of distributive laws of the Cartesian product with union and intersection. And also, like, here's a relation between the Cartesian product and set difference. So to work with these, we have to, work with ordered pairs. So, so this, you should read this example here as you're trying to work on the homework. This should be helpful to you see how we make proofs involving Cartesian products, all right? Now, all right. Oops, that's the end of the chapter, but going back a set here, I need to make a correction here. There's some horrible things in this definition. Horrible. First of all, number one is supposed to say, the second part of it is d of xy is equal to 0 if and only if x is equal to y. That's what's supposed to be in number one, for one thing. So this is what's called a metric. The metric is a way of abstracting the concept of distance on a space. And we'd say that the distance has to be 0 or positive, for one thing. And then the other part of this definition, when stated properly, is that the distance from x to y is 0 only if what? Only if x and y are equal. They have to be the same point. Only a point is the same is 0 distance from itself, all right? That's what's supposed to be there. That's a typo. And this down here, this is just not true. The distance from x to y plus the distance from y to z should be greater than